In 1964, in a field in Holmdel, New Jersey, two radio astronomers named Arno Penzias and Robert Wilson climbed inside a horn antenna and began cleaning it out by hand. They were not doing science, they were doing maintenance. Their instrument, a great aluminum ear built by Bell Telephone Laboratories to listen for signals bounced off early communications balloons, was picking up a faint hiss that would not go away, and they had run out of explanations for it. So they checked the wiring. They checked the joints. They found a pair of pigeons nesting in the throat of the antenna, evicted them, and scraped out the droppings the birds had left behind on the metal. The hiss remained. It came from every direction in the sky, at every hour, in every season, with no source they could point to, and no way to shut it off. What the two men had failed to clean out of their antenna was the oldest light in existence. It is called the cosmic microwave background, and it is the boundary of everything we are able to see. Every diagram of the observable universe you have ever looked at ends at that light. It is the edge of the map, and nobody can tell you how far away it is. That is not a gap in the data. It is not a problem waiting on a better telescope. There are 4 different ways to define the distance to that light. All 4 are legitimate. All 4 are in use in the professional literature, and they do not agree with each other by a factor of 2 or 3. They disagree by 6 orders of magnitude. Ask how long the light has been traveling, and multiply by its speed. You get 13.8 billion light-years. Ask where the material that emitted it has drifted to now, after all the intervening space has stretched underneath it, and you get roughly 45.6 billion light-years. Ask how far away it looks, judging by the apparent size of the features printed across it, and the answer comes back at about 42 million light-years. Ask how far away it looks, judging instead by how badly the light has been dimmed, and you get something on the order of 50 trillion. Same object, 4 answers. Not one of them is an error. So when you hear that the observable universe is 93 billion light-years across, understand what has happened in that sentence. Someone has quietly selected one of those 4 definitions and discarded the other 3, and then handed you the result, as though it were a measurement of a room. The third answer is the one that should stop you. Taken at face value, it says that the hot plasma that released that light was, at the moment it released it, only about 42 million light-years from the matter that would eventually become the Earth, the Sun, and everyone who has ever lived. That is roughly the present distance to the Virgo cluster. The most distant thing in the observable universe was, when it spoke, practically a neighbor. And it is not an edge in any case. Nothing ends there. The transition that released that light, the moment when the universe cooled enough for atoms to hold together and photons to travel freely, was not an instant. It took something on the order of 100,000 years. The so-called surface of last scattering is therefore not a surface at all. It is a fog bank with thickness, and it recedes. Every year, we are looking at a slightly different shell of it. We cannot even agree on the scale of the ruler. The Planck satellite, measuring that ancient light directly, gives an expansion rate near 67 kilometers per second per megaparsec. Teams, measuring the nearby universe with variable stars, including the group led by the astronomer Adam Rees, keep returning values closer to 73. That disagreement has survived 20 years of improved instruments, and it is worth roughly 9% of the size of everything. Billions of light-years, hanging on which method you trust. None of this is a scandal. It is simply what it looks like to measure something from the inside, with no outside to step into. But argue about that number long enough, and you will miss the thing that should actually unsettle you, because the size of the universe is not the frightening part. The frightening part is what is inside it. Take everything, every star in every galaxy, every planet, every moon, every asteroid, every grain of dust drifting between them, every atom of hydrogen in every nebula. Spread all of it out evenly across all the volume that contains it, and current estimates of the average density of ordinary matter come to something close to 1 atom for every 4 cubic meters of space. 1 atom, 4 cubic meters. That is the universe, averaged honestly. Hold that against the air in front of your face. A single cubic meter of ordinary room air contains something in the region of 25 septillion molecules. That 1 cubic meter, the volume of empty-seeming air you could wrap your arms around, holds more particles than there are stars in every galaxy in the observable universe combined. By a factor of about 100. You are, right now, standing inside the densest thing you will ever encounter. Before we go further, if this is the kind of thing you want to fall asleep to, a like, a comment, or a subscribe would mean a great deal to me. To understand emptiness, you first have to see the opposite of it, and the opposite of it is not the Earth, and it is not the Sun, and it is not the galaxy. It is a globular cluster. In 1677, from the island of St. Helena in the South Atlantic, the young English astronomer Edmund Halley was cataloguing the southern sky when he noted that one object in the constellation Centaurus was not behaving like a star. Ptolemy had listed it as a star 15 centuries earlier. Through Halley's telescope, it refused to sharpen to a point. It stayed soft and round and faintly grainy at the edges, as though something had smudged it. It had been smudged by roughly 10 million suns. The object is now called Omega Centauri, and it is the largest globular cluster orbiting the Milky Way. It is a ball of ancient stars, about 150 light-years across, sitting some 17,000 light-years from here, held together by nothing but its own gravity. The stars in it are old, close to 12 billion years in most estimates, which means they formed while the galaxy itself was still assembling. Some researchers now think it may not be a cluster at all, but the stripped core of a small galaxy the Milky Way swallowed long ago. There are around 150 known globular clusters bound to our galaxy. They do not sit in the disk with everything else. They orbit above and below it in a great spherical swarm, and that geometry turned out to matter enormously. In 1918, the astronomer Harlow Shapley, working at the Mount Wilson Observatory, mapped the distances to those clusters using pulsating variable stars as distance markers. He found that the swarm was not centered on us. It was centered on a point, thousands of light-years away, in the direction of Sagittarius. That was the moment humanity was moved off-center, not by philosophy, by counting clusters, but it is the interiors of these objects that concern us here, because a globular cluster core is the densest stellar environment in the observable universe outside the immediate neighborhood of a black hole. In the crowded center of a cluster like 47 Tucanae, which holds something on the order of 1 million stars inside a sphere roughly 120 light-years wide, the density of stars is measured in the thousands per cubic parsec. Out here, in the ordinary galactic disk, the equivalent figure is a fraction of 1. We can put a distance on it. In the core of a rich globular cluster, the typical separation between neighboring stars is thought to be on the order of 1/10 of a light-year. That is about 6,000 astronomical units. It is roughly 200 times the distance from the Sun out to Neptune. Try to stand there. Estimates of what the sky would look like from a planet near such a core suggest hundreds of stars brighter than Venus ever appears from Earth, scattered across the whole dome of the sky at once. There would be no true night. The ground would hold a permanent soft illumination, bright enough to read by, coming from every direction and never quite going out. Sunset would change the color of the light and almost nothing else. And here is the thing that makes these places genuinely different from the rest of the universe. In a globular cluster core, stars actually run into each other. Everywhere else, this effectively never happens. Here, over billions of years, it happens often enough to leave visible wreckage. Astronomers find stars in these cores called blue stragglers, which are hotter, brighter, and apparently younger than every star around them, in a population where everything formed at the same time and nothing young should exist. The leading explanation is that they are collision products, or the result of one star stripping material from a close companion. They are stars that have been in an accident and survived it. The Hubble Space Telescope has imaged them in cluster after cluster. Some cores appear to have collapsed inward entirely, packing stars so tightly that the brightness profile spikes at the very center, rather than leveling off. There are a few environments that press even harder. Near the center of our own galaxy sits the Arches cluster, a young and extraordinarily compact knot of massive stars. And in the large Magellanic Cloud, there is a cluster called R136, embedded in the Tarantula Nebula, which contains some of the most luminous stars ever identified. These are short-lived places. Their brightest members will be gone in a few million years. The globular clusters, by contrast, have been holding themselves together since before the Sun existed, slowly leaking stars from their outer edges as the galaxy's tides pull at them, gradually evaporating over timescales that make stellar lifetimes look brief. This is the maximum. This is as crowded as the universe gets. 10 million stars in a ball you could cross at the speed of light in a century and a half, close enough together to collide. Now hold that against a human standard. 6,000 astronomical units is roughly 900 billion kilometers. If you were on a planet in the densest part of Omega Centauri and you set out for the nearest neighboring star at the speed of the fastest object humanity has ever launched, you would not arrive within a recorded human history. You would not arrive within 10 of them. The sky above you would be blazing with stars, and every single one of them would be a journey of many thousands of years. There is a way to make this precise, and it is worth doing once, because the answer sets the ceiling for everything that follows. Take a star of ordinary size, something close to our own Sun, a little under 1.5 million kilometers wide. Now take the volume of space it has to itself in that cluster core. Work out what fraction of that volume the star physically occupies. The answer is about 1 part in a quintillion. A 1 followed by 18 zeros, and the star is the 1. Even here, even in the single most tightly packed collection of matter that stars are capable of forming, in a place bright enough to abolish night and dense enough for suns to strike each other, the matter is a rounding error against the space. If you dropped into that core at a random point and looked around, the overwhelmingly likely outcome is that you would be nowhere near anything at all. That is the crowded case. That is the best the universe can do. The distances only grow from here, and they grow faster than intuition can follow. Every step outward from this point multiplies the gap between one thing and the next, and the objects themselves do not grow with it. A star in a cluster core and a star drifting alone between galaxies are the same size. Only the space around them changes. So begin here, in the brightest, most crowded, least lonely place that exists, and remember what it felt like. Because we are about to leave it, and we are not coming back to anything like it. On the 7th of October 2015, a filmmaker named Wiley Overstreet and his collaborator Alex Gorosh drove into the Black Rock Desert in Nevada with a group of friends, a set of lights, and a plan that most people would have called excessive. They wanted to build a scale model of the solar system, not a diagram, a model with nothing left out and nothing shrunk to fit. They chose a marble, roughly 1.5 centimeters across, to stand in for the Earth. At that scale, the model needed a circle of empty desert, 11 kilometers wide. Neptune's orbit alone required a track they had to drive to complete. They spent the day marking it out, and then they waited for dark and drove the orbits with lights on the vehicles so that a camera on a nearby mountain could see the shape of the thing all at once. What the camera recorded was a set of enormous glowing rings, enclosing almost nothing. The marble that was the Earth was invisible from the camera position. So was everything else. This is the first honest picture most people ever see of the place they live. And the reason is simple. Every solar system diagram ever printed is a lie of composition. The planets are drawn too big, the orbits are drawn too close, and the gaps are compressed until the page can hold them. It is a necessary lie. It is also the reason almost nobody has an accurate sense of where they are. So let us undo it, carefully, with real numbers. The Sun contains about 99.8% of all the mass in the solar system. Everything else, every planet, every moon, every asteroid, every comet, every ring particle and dust grain and lump of ice out to the furthest edge makes up the remaining fraction. And most of that remainder is Jupiter. If you removed the Sun and Jupiter from the accounting, the entire rest of the solar system, including the ground beneath you, amounts to a bit of debris. The Earth is 12,742 kilometers across. The Sun sits an average of about 150 million kilometers away. That single gap, the one we call an astronomical unit, is nearly 12,000 Earths laid end to end. Light crosses it in a little over 8 minutes, and light is the fastest thing there is. Here is a comparison that people usually refuse to believe on first hearing. Take every planet in the solar system: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Line them up, side by side, touching, largest to smallest. The total length of that line comes to roughly 380,000 kilometers. The Moon orbits at an average distance of about 384,000 kilometers. Every planet in the solar system fits in the gap between the Earth and its own moon, with room left over. That gap is the furthest any human being has ever traveled from home. 24 people have crossed it. 12 have stood at the far end of it. And it is a distance that could swallow the entire planetary content of the solar system without touching the sides. Go further out, and the emptiness stops being a curiosity and starts being a genuine engineering surprise. Between Mars and Jupiter lies the asteroid belt, which in the popular imagination is a hazard, a tumbling wall of rock that a ship has to weave through. In reality, the belt is one of the emptiest things ever named. Estimates put the total mass of everything in it at something like 4% of the mass of the Moon, spread across a ring hundreds of millions of kilometers wide. The typical separation between one asteroid large enough to notice and the next is measured in millions of kilometers. We know this because we tested it. In 1972, the National Aeronautics and Space Administration launched Pioneer 10, and mission planners genuinely did not know whether it would survive the crossing. Some estimates gave it poor odds. It went through without incident. So did Pioneer 11. So did both Voyager spacecraft, and Galileo, and Cassini, and every probe since. If you were placed at a random point inside the asteroid belt, you would almost certainly be unable to see a single asteroid with the naked eye. Keep going. Neptune orbits at 30 astronomical units. Beyond it is the Kuiper Belt, the region the Dutch-American astronomer Gerard Kuiper wrote about in 1951, a broad zone of icy bodies stretching out to around 50 astronomical units, containing Pluto and Eris and Makemake, and hundreds of thousands of smaller objects. Current estimates of its total mass come in at a few percent of the Earth's, possibly less. It is a belt in the way a scattering of grains across a football field is a belt. In 2019, the New Horizons spacecraft flew past an object out there called Arakoth, a small reddish body shaped like two joined lobes, more than 6 billion kilometers from the Sun. The signal announcing the encounter took over 6 hours to reach Earth, traveling at the speed of light. To find that one object in that volume, the mission team had to search with the Hubble Space Telescope for years, and they nearly did not find anything at all within reach of the spacecraft's remaining fuel. And then there is the Oort cloud. In 1950, the Dutch astronomer Jan Oort proposed that the long-period comets that occasionally fall into the inner solar system must come from somewhere, and that the somewhere must be a vast spherical reservoir surrounding the Sun at enormous distance. The current picture places its outer regions somewhere between 10,000 and 100,000 astronomical units out. Nobody has ever directly observed it. It is inferred entirely from where comets come from and how they arrive. Estimates suggest it may contain trillions of icy bodies. That sounds crowded. It is the opposite. Spread trillions of objects through a sphere with a radius approaching a light year, and the average distance between one comet and its nearest neighbor comes out in the region of tens of millions of kilometers. You could stand on one and see nothing else. Not one other member of the swarm you belong to. The Sun would be a bright star among the other bright stars, giving no useful heat and casting no shadow you could measure. That is the outer edge of the Sun's influence, a shell of ice so sparse that its inhabitants are, from each other's point of view, alone. So look at what the solar system actually is. One star, holding almost all the mass. 8 planets, which collectively fit in the gap to the Moon. A belt of rocks a spacecraft can cross without aiming. A ring of ice we can barely find things in. A halo of comets that has never been seen, and around all of it, filling the volume between every one of those objects, a nothing so complete that the phrase empty space is not a metaphor. It can be quantified, and the quantity is absurd. Draw a sphere with the Sun at the center and Neptune's orbit as the surface. Then work out how much of that sphere is filled with anything solid or gaseous or liquid. How much of it is the Sun, the planets, the moons, the rocks? The figure comes out at roughly 1 part in 300 billion, and almost all of that 1 part is the Sun by itself. We have also felt the edge of it directly. In August 2012, Voyager 1 crossed the heliopause, the boundary where the outward pressure of the solar wind finally gives way to the gas between the stars. Its instruments registered the change as a jump in the density of charged particles and a shift in the magnetic field. That boundary sits around 120 astronomical units out. Voyager 1 took 35 years to reach it. It will need another 300 centuries to cover the distance to the nearest star, and it is not aimed at one. There is a version of this that Carl Sagan understood better than anyone, and he arranged for us to see it. In 1990, at his urging, Voyager 1 turned its camera around from a distance of about 6 billion kilometers and photographed the Earth. The result is a single pale point occupying less than 1 pixel, sitting inside a scattered band of sunlight in the camera optics. The photograph is famous for what it shows. It should be more famous for what it does not show. There is no solar system in that image. There is no Sun with neat concentric rings, no Jupiter, no belt of asteroids, no visible structure of any kind. There is a dark frame and 1 dot, and that is the entire content of our neighborhood, from a distance that light crosses in 5.5 hours. 5.5 hours. Now multiply by 7,000, and you have reached the nearest other star. In 1930, at the Lick Observatory in California, the Swiss-American astronomer Robert Trumpler was studying open star clusters and running into a contradiction he could not resolve. He had two ways of estimating how far away a cluster was. One used the apparent brightness of its stars. The other used its apparent size. For nearby clusters, the two methods agreed. For distant ones, they did not, and the disagreement grew steadily worse with distance, always in the same direction. The distant clusters looked too faint for their size. Trumpler drew the only conclusion the data allowed. Something was in the way. Something was thinning the light on its journey, a little more for every parsec it crossed, and that something had to be spread through the galaxy itself. He had found the interstellar medium, and in doing so, he established that the space between the stars is not, strictly speaking, empty, which turns out to be a far more disturbing fact than the alternative, because here is what it contains. In the general disk of the Milky Way, the average density of the interstellar medium is somewhere around 1 atom per cubic centimeter, mostly hydrogen. In the denser molecular clouds where stars are born, it climbs into the thousands or millions of particles per cubic centimeter. In the hot, ionized regions carved out by exploded stars, it falls to something like 1 atom in every 1,000 cubic centimeters. Now compare that to what we can achieve deliberately. The best ultra-high vacuum chambers ever built, the ones used for surface physics and particle accelerators, evacuated with enormous effort and enormous expense, still hold something on the order of tens of thousands of particles per cubic centimeter. Read that again. The finest vacuum human engineering has ever produced is tens of thousands of times denser than ordinary interstellar space. We cannot manufacture the emptiness that is the default condition of our own galaxy. We are not remotely close, and we happen to live somewhere unusually empty, even by that standard. The Sun sits inside a cavity called the local bubble, a region roughly 1,000 light-years across, where the density falls to something near a 20th of an atom per cubic centimeter. In 2022, a team led by the astronomer Catherine Zucker at the Center for Astrophysics published an analysis in the journal Nature Reconstructing Its History. Their reconstruction suggests it was hollowed out by a series of supernovae beginning roughly 14 million years ago, which swept the gas outward into an expanding shell, and that essentially all the young star-forming regions near us sit on the surface of that shell. We are living inside a blast cavity, and the nurseries are on its walls. So that is the medium. Now the distances. The nearest star system to the Sun is Alpha Centauri, and the nearest individual star in it is Proxima Centauri, a small red dwarf about 4.2 light-years away. That is roughly 40 trillion kilometers. There is no way to make that number mean anything by stating it, so convert it. In the last section, the marble in the desert stood for the Earth. Change scale entirely. Shrink the whole solar system, all the way out to Neptune's orbit, until it is the size of a coin lying on the ground in front of you. Everything we have discussed so far, the Sun, all 8 planets, the asteroid belt, the crossing that took Voyager 1 12 years, now fits under your thumb. At that scale, Proxima Centauri is another coin, roughly the length of a football field away. And between the two coins, there is nothing, not a dim object waiting to be discovered, not a faint smear of debris. There is gas at a density we cannot reproduce in a laboratory, and there is dust, and there are photons passing through, and the total mass of all of it in that stretch would not build a hill. Voyager 1 is moving at about 17 kilometers per second, which is fast enough to cross the United States in 4 minutes. If it were aimed directly at Proxima Centauri, It would need something in the region of 70,000 years to arrive. Anatomically modern humans have existed for perhaps 300,000 years. The journey to the nearest star, at the speed of the fastest thing we have ever thrown, occupies a quarter of the entire existence of our species. Now scale that up to the galaxy. The Milky Way is a disk somewhere between 100,000 and 200,000 light-years across, depending on where you decide the edge is, and only about 1,000 light-years thick through most of it. It contains, by current estimates, somewhere between 100 and 400 billion stars. That is a genuinely enormous number of objects, and it produces a genuinely misleading intuition, because our images of the galaxy, the artist's impressions, the wide-field photographs of other spirals, show a continuous glow, a solid thing, a structure. The glow is an artifact of distance. Put 100 billion pinpoints far enough away, and they blur into a sheet. Here is the actual density. In our neighborhood, there is roughly 1 star for every 300 cubic light-years of space. Not 1 star per cubic light-year, 1 star per 300 of them. And a cubic light-year is a volume so large that the solar system, out to the Oort cloud, occupies a small fraction of it. If you were dropped at a random point in the galactic disk, the odds are overwhelming that you would find yourself in the dark, with no star closer than several light-years, and you would have no way to tell from your surroundings whether you were in the Milky Way at all. You could not feel the spiral arms. They are not physical structures made of tightly packed stars. They are density waves, patterns of slightly increased compression moving through the disk, lighting up because they trigger star formation, not because the stars there are meaningfully crowded together. The arms look bright for the same reason a traffic jam looks dense from a helicopter. The cars are still cars, with gaps between them. There is exactly one region of the galaxy where this is not true, and it is worth naming so that the exception does not go unmentioned. In the innermost light-year, around the galactic center, stars are packed more tightly than in any globular cluster core, orbiting a black hole of about 4 million solar masses. 2 teams, one led by the astronomer Andrea Ghez in the United States, and one by the astrophysicist Reinhard Genzel in Germany, spent decades tracking individual stars through that region, watching one of them complete an entire orbit around an object they could not see. The work earned them a share of the Nobel Prize in Physics in 2020. That inner light-year is the most crowded volume in the Milky Way, and it constitutes an unimaginably small fraction of it. Everywhere else, the emptiness is so reliable that in the entire lifetime of the Sun, nothing has ever come close to us. The Sun takes something like 230 million years to complete one orbit of the galaxy. It has made around 20 of those circuits since it formed. In all that travel, through all those encounters, the closest known stellar approach on record is a small binary system catalogued by the astronomer Ralph Dieter Schultz, which the astronomer Eric Mamajek and colleagues calculated in 2015 to have passed within roughly 1 light-year of us about 70,000 years ago. That is the near miss, a light-year. Our ancestors were alive for it, and nothing happened. We have even watched objects cross this emptiness from outside it. In 2017, an astronomer named Robert Werrick, working with the Panoramic Survey Telescope and Rapid Response System in Hawaii, identified an object on a trajectory that could not be closed. It had come from interstellar space, and it was leaving again. It was named Oumuamua. It was a few hundred meters long, and it passed through the inner solar system in a matter of weeks. A second interstellar visitor, a comet, followed in 2019, and a third was identified in 2025. 3 objects, in all of recorded history, from a galaxy of hundreds of billions of stars, each of which has presumably been shedding material for billions of years. That is the arrival rate across the great nothing between the stars. Not because the galaxy is not producing debris, because the volume it has to cross is so large that almost nothing ever finds anything. In 1912, at the Lowell Observatory in Flagstaff, Arizona, an astronomer named Vesto Slipher pointed a telescope at the faint oval smudge in the constellation Andromeda and spent several nights collecting enough light to spread into a spectrum. Nobody yet knew what the smudge was. The prevailing view held that it was a cloud of gas inside our own galaxy, possibly a solar system in the act of forming. What Slipher measured was motion. The lines in the spectrum were shifted toward the blue end, which meant the object was approaching. And it was approaching fast, faster than anything anyone had ever measured, around 300 kilometers per second. It took another decade for Edwin Hubble to establish what the object actually was, a separate galaxy, comparable to our own, more than 2 million light-years away. But Slipher's measurement stood, and it stands today. The Andromeda galaxy is falling toward us. 2 galaxies, each containing hundreds of billions of stars, are on a collision course. And here is the part that ought to be impossible. When they meet, the number of stars expected to physically strike one another is, for practical purposes, 0. Not small, not manageable, effectively none. In the standard simulations of a galaxy merger, individual stellar collisions are so rare that they are treated as negligible. 2 objects containing something like 500 billion stars between them will pass through each other, and the stars will simply thread between one another like 2 flocks of birds occupying the same sky. You already know why, because we established the density in the last section. But the numbers are worth making explicit, because this is the moment the abstract becomes vivid. A star is roughly 1 million kilometers across. In the disk of a galaxy, the nearest other star is roughly 40 trillion kilometers away. The target is about 40 million times smaller than the gap. To hit something, you have to aim at something, and there is nothing to aim at. So during a galactic merger, the stars do not collide. What collides is the gas. This is a real distinction with observable consequences, and it is where the interesting physics lives. Stars are compact and separated. Interstellar gas clouds are diffuse, enormous, and continuous. They can be hundreds of light-years across. 2 galaxies passing through one another slam their gas reservoirs together, and the gas has nowhere to go. It compresses, it shocks, it cools, and it collapses into new stars at rates far above normal. We can watch this happening. In the constellation Corvus, there is a pair of interacting galaxies called the antennae, named for the 2 enormous tails of stars flung out by the encounter. Hubble's Space Telescope imaging of the collision region shows thousands of bright young star clusters that did not exist before the 2 galaxies met. The Atacama Large Millimeter Array has since mapped the dense molecular gas in the overlap region in detail. The merger is not destroying the galaxies, it is making them fertile. The stars, meanwhile, do not notice. Their orbits are rearranged by the changing gravitational field. Their positions are scrambled. Almost none of them touch. Now, the honest complication, because the Andromeda collision has become one of the most confidently repeated facts in popular astronomy, and the confidence is no longer warranted. The prediction of a head-on merger depends on knowing Andromeda's sideways motion across the sky, not just its motion toward us. That sideways component is extraordinarily difficult to measure at a distance of 2.5 million light-years, and it is the number that decides whether the 2 galaxies strike each other or swing past. In 2025, a team led by the astrophysicist Till Sawala published an analysis in Nature Astronomy incorporating updated measurements and the gravitational influence of the other large members of our neighborhood, particularly the Large Magellanic Cloud. Their conclusion was that over the next 10 billion years, a merger is close to a coin flip. Roughly even odds, not the certainty that has been repeated for 2 decades. We do not know whether the collision happens. We know only that it is possible, that it would take billions of years, and that if it does occur, essentially nothing in either galaxy will be struck. Suppose it does happen. It is worth asking what it would be like to be standing on a world underneath it, because the answer says something about the word collision that no diagram conveys. You would not see an impact. There is no impact. A galactic merger is not an event, it is a condition, and it lasts for billions of years. The first sign would be a slow brightening of one region of the night sky over tens of millions of years, as a second galaxy resolved from a smudge into a spread of light large enough to cast a shadow. Then, a long period in which 2 great bands of stars crossed the sky at once. Then a gradual scrambling, over a timescale 1,000 times longer than our species has existed, until the ordered disk was gone and the sky was an unstructured glow in every direction. Nothing would strike the ground. No star would arrive. The night would change slowly enough that no single generation would notice, and it would take longer to complete than the Earth has so far existed. In 2008, the astrophysicists Thomas Cox and Abraham Loeb ran detailed simulations of this outcome and gave the merged remnant a name that has stuck in the literature. Their models suggest the final object would be an elliptical galaxy, a featureless swarm rather than a spiral, its gas largely spent on one great burst of star formation and then exhausted. Elliptical galaxies of exactly this kind fill the nearby universe. Every one of them is a merger that finished. They are not ruins. They are simply what is left when the structure is stirred away and no new stars are being made. There is one more layer, and it makes galaxies emptier still. Everything we have counted so far, the stars, the gas, the dust, is not what a galaxy is mostly made of. Since the 1930s, when the astronomer Fritz Zwicky noticed that galaxies in the Coma cluster were moving far too fast to remain bound by their visible mass, and more decisively, since the 1970s, when the astronomer Vera Rubin and her collaborator Kent Ford measured the rotation of spiral galaxies and found that the outer regions were orbiting at speeds the visible matter could not explain, we have known that the luminous part of a galaxy is a minority component. The current picture holds that a galaxy like ours sits inside a roughly spherical halo of dark matter, extending far beyond the visible disk, outweighing all the stars and gas by something like 5-to-1. Nobody knows what it is made of. Every attempt to detect a particle of it directly has so far come back empty, which means the object you see in a photograph of a spiral galaxy, that bright pinwheel, that structure that looks like a thing, is a small luminous contamination inside a much larger sphere of something we cannot see, and the sphere itself is diffuse beyond any ordinary meaning of the word. Estimates of the local dark matter density come out at a fraction of a proton mass per cubic centimeter. If dark matter is a particle, then several billion of them are passing through your body every second, and not one of them has ever been caught doing it. So take the whole accounting. A galaxy is 100 billion stars, separated by tens of trillions of kilometers each, embedded in a gas so thin we cannot manufacture it, suspended inside a halo of something invisible and undetectable that outweighs all of it. And the galaxies themselves are, on the scale we are about to move to, the crowded places. For most of the 20th century, cosmologists had a bookkeeping problem they could not solve. and it was not a small one. They could calculate, from the physics of the first few minutes after the Big Bang, and from the pattern of the oldest light, how much ordinary matter the universe ought to contain. Then they went out and counted it. They added up the stars in the galaxies, the gas inside them, the hot plasma in galaxy clusters, everything that gave off light or absorbed it. The sum came out short. Roughly half the ordinary matter in the universe was missing. Not dark matter, which is a separate and stranger problem. Ordinary atoms, protons and neutrons of the kind that make up a chair, unaccounted for. The leading suspicion was that the missing material was not missing at all, but simply too diffuse and too hot to see. It was thought to be lying in the space between the galaxies, spread so thin that it emitted almost nothing and absorbed almost nothing. Invisible, not because it was hidden, but because there was not enough of it in any one place to notice. Confirming that required a genuinely strange instrument, and the instrument turned out to be an exploding object in another galaxy. Fast radio bursts are millisecond flashes of radio energy arriving from cosmological distances, first identified in 2007, and their origins are still not fully settled. What matters here is what happens to them in transit. A radio burst leaves its source as a sharp pulse across many frequencies. As it crosses intergalactic space, the free electrons it passes through slow the lower frequencies slightly more than the higher ones, and the pulse arrives smeared out in time. The size of that smear is a direct measure of how much material the signal traveled through. In 2020, a team led by the astronomer Jean-Pierre Macquarque, using the Australian Square Kilometre Array Pathfinder, published a measurement in the journal Nature using localized bursts to weigh the intervening medium. The result matched the amount predicted from the early universe. The missing matter was where it had been suspected of being. It was in the space between everything. So now we can state the density of intergalactic space, and this is the number that should be carried out of this section. The average density of ordinary matter in the intergalactic medium is somewhere on the order of a single atom per cubic meter. In some regions, considerably less, 1 atom, in a volume you could stand inside. Compare that to the interstellar space we discussed earlier, which held roughly 1 atom per cubic centimeter. There are 1 million cubic centimeters in a cubic meter. The space between galaxies is therefore something like 1 million times emptier than the space between stars. And the space between stars was already a vacuum we cannot reproduce with any technology we possess. And most of it is not cold. Much of that intergalactic material sits at temperatures between about 100,000 and 10 million degrees, heated by shocks as gravity pulls it around. It is called the warm-hot intergalactic medium. It is simultaneously hotter than the surface of the Sun and so sparse that a spacecraft passing through it would register essentially nothing. Temperature at that density is a statement about how fast individual particles are moving, not about how much heat there is to transfer. There is nothing there to burn you. There is a second way we see this material, and it is older and more elegant. Point a telescope at a quasar, an extremely luminous object in the distant universe, and spread its light into a spectrum. What comes back is not a smooth band. It is a band cut through with hundreds of narrow dark lines, each one produced by a cloud of intergalactic hydrogen the light passed through on its way here, each at a slightly different distance, and therefore a slightly different shift in wavelength. Astronomers call it the Lyman Alpha Forest. The physicists John Barcall and Edwin Salpeter predicted the effect in 1965, and the astronomer Roger Linz observed it a few years later. Every dark line in that forest is a shadow of something we cannot otherwise see. A single quasar spectrum can carry the fingerprints of hundreds of separate clouds strung across billions of light-years. It is one of the few situations in science where the absence of light is the data. The same is true inside galaxy clusters, where the gas is denser and hotter still. When X-ray telescopes were first flown above the atmosphere in the early 1970s, they found that clusters of galaxies glow in X-rays across their whole volume, filled with plasma at tens of millions of degrees. The surprise was the accounting. In a large cluster, that thin, hot gas outweighs all the stars in all the member galaxies by a factor of several. The galaxies, which look like the contents of the cluster, are a minority of its ordinary matter. Most of it is the nearly invisible material in between. Now the distances, which are what the emptiness is measured across. Our galaxy belongs to a small collection called the local group. It contains, by current counts, somewhere north of 80 members, but the accounting is misleading. Nearly all of them are dwarf galaxies, faint and small. There are only 3 large members, the Milky Way, Andromeda, and the considerably smaller Triangulum galaxy. Everything else is a fragment. Andromeda is about 2.5 million light-years away. That is the near neighbor. That is the close one. It takes light 2.5 million years to cross the gap between our galaxy and the next comparable object. And in that entire span, there is, on average, about 1 atom per cubic meter. There is a way to feel that gap. The Milky Way is about 100,000 light-years across. The distance to Andromeda is roughly 25 times that. So if you shrank our galaxy to the size of a dinner plate, the next comparable galaxy would be a second dinner plate, about 7 meters away, and the space between the 2 plates would contain, at true scale, a few dozen crumbs. Beyond the local group, the distances become unrelenting. The nearest large cluster of galaxies, the Virgo cluster, lies around 54 million light-years away. The Coma cluster sits at roughly 320 million. Those are not multiples of the Andromeda gap. They are multiples of multiples, and the objects being separated have not grown at all. But there is a thought experiment here that captures the situation better than any distance, and it involves the loneliest stars in existence. When galaxies pass close to one another inside a cluster, the tidal forces strip stars out of them and fling them into the space between. Over billions of years, a great many stars accumulate this way. Observations of the Virgo cluster and others have detected a faint diffuse glow, filling the volume between the member galaxies, produced by stars that belong to no galaxy at all. In some clusters, estimates suggest this intra-cluster light accounts for something on the order of 10% of the total starlight. Imagine a planet orbiting one of those stars. Its sky would contain its own sun, and effectively nothing else. There would be no band of the Milky Way overhead, no scattering of neighboring suns, no constellations, because there would be no other stars close enough to resolve into points of light. The night sky would be black, with a handful of faint smudges in it. Entire galaxies, each containing hundreds of billions of stars, reduced by distance to something dimmer than the dimmest star you can see from Earth on the clearest night. A civilization on such a world would have no reason to invent astronomy. It would have no way to measure the distance to anything. It would look up and see darkness, and it would be correct. That is not a hypothetical arrangement. Those stars exist, in large numbers, right now, and they have been drifting between the galaxies of the Virgo cluster for longer than the Earth has had oceans. And we are still, at this point, only describing the inside of a cluster. Clusters are the dense places. They are where matter has succeeded in gathering itself. On the scale we reach next, the entire local group and everything in it becomes a single point in a diagram, and the diagram is mostly blank. In 1986, at the Harvard-Smithsonian Center for Astrophysics, 3 astronomers named Valerie de Lapparent, Margaret Geller, and John Huchra finished plotting the results of a redshift survey and looked at what they had drawn. The technique was straightforward and enormously laborious. Take a strip of sky, measure the spectrum of every galaxy in it, one at a time, night after night, to determine how fast each one is receding. Convert that speed into a distance. Then plot each galaxy as a dot at its correct distance and direction, producing not a photograph, but a map, a slice through the actual 3-dimension of matter. Nobody knew what the map would look like. The reasonable expectation, held by most cosmologists at the time, was that galaxies would be scattered more or less at random, clumping a little here and there, filling the slice fairly evenly. The slice was not filled. It was full of holes. What the plot showed was galaxies strung along thin, curving arcs, with enormous round emptinesses between them, as though the universe were a mass of soap bubbles, and the galaxies were confined to the surfaces where the bubbles met. In one region, the arrangement of dots happened to resemble a human figure with outstretched arms, and it became known informally as the Stick Man. 3 years later, Geller and Huchra reported a coherent sheet of galaxies more than 500 million light-years long, which they called the Great Wall. Neither structure was supposed to exist. Both were there. That map was the first clear view of what is now called the cosmic web, and it is the correct, large-scale picture of the universe, the one that replaces every image you have of galaxies scattered evenly through space, like stars in a photograph. Here is the structure it describes. Matter is arranged in filaments, long, thin threads of galaxies and gas and dark matter, stretching for hundreds of millions of light-years, some of them longer. Where filaments meet, they form nodes, and the nodes are the great clusters of galaxies, Virgo, Coma, and hundreds more. Between the filaments lie flat sheets, sometimes called walls, which are broad and thin and populated, and enclosed by all of that, occupying the space the filaments and walls define, are the voids. The voids are the story. Everything else is the packaging. Current estimates suggest that voids occupy something in the region of 80% of the total volume of the universe, and by some measures, considerably more. The exact figure depends on where you draw the boundary of a void, which is a real and unresolved definitional problem. But the qualitative conclusion is not in dispute, and has not been for decades. The overwhelming majority of the universe's volume is void. The overwhelming majority of its matter is not. It is worth pausing on how lopsided that arrangement is, because volume and content have come apart almost completely. A void is not merely a region with fewer galaxies. In the deepest parts of a large void, the density of matter falls to something like 1/10 of the cosmic average, and the cosmic average was already 1 atom per cubic meter. The filaments, meanwhile, can run tens or hundreds of times denser than average, and the cluster cores at the nodes denser still. All of the interesting chemistry, all of the stars, all of the planets, every process that has ever produced anything is confined to the narrow, high-density minority of the volume. If you selected a point at random inside the observable universe, genuinely at random, with every cubic meter given equal weight, you would land in a void. Not occasionally, almost every time, you would find yourself in a place where the nearest galaxy is tens of millions of light-years off, where the local matter density is a fraction of an already unimaginably small number, and where nothing has happened, and nothing will happen, for the remaining lifetime of the cosmos. This has a consequence that takes a moment to absorb. Every image of the cosmos that has ever moved you, the deep field photographs, the spiral galaxies, the star-forming pillars, the clusters, bending light behind them, is a photograph of the exception, not a representative sample, not a typical region. The bright, structured, interesting universe is a thin residue clinging to the boundaries of the empty universe, and the empty universe is the main body of the thing. Matter is not what the cosmos is made of. Matter is what is left over at the edges of where it is not. We know the structure is real because we have now mapped it at scale, and because it emerges unbidden from simulations. In 2005, a group called the Virgo Consortium, led by the astrophysicist Volker Springel, ran a calculation known as the Millennium Simulation, following more than 10 billion particles of dark matter as gravity acted on them from just after the Big Bang to the present day. They did not put a web into the initial conditions. The initial conditions were almost perfectly smooth, tiny density fluctuations of the kind the oldest light shows us, a difference of parts in 100,000. Gravity did the rest. Slightly denser regions pulled in material and grew denser. Slightly emptier regions gave up their material and grew emptier. Over billions of years, the tendency compounded, and the smooth beginning collapsed into filaments and nodes and voids that match the observed sky in statistical detail. The universe was not built empty. It emptied itself. The voids were once ordinary regions that simply lost, and every particle they surrendered went to make the filaments that now surround them. Mapping this has become one of the largest projects in science. The Sloan Digital Sky Survey, operating from New Mexico since 2000, measured spectra for millions of galaxies and produced the three-dimensional maps most people have now seen. The 2-degree field survey in Australia did the same from the southern hemisphere. More recently, the Dark Energy Spectroscopic Instrument, mounted on a telescope at Kitt Peak in Arizona, has been measuring tens of millions of galaxy distances to build the largest three-dimensional map of the universe yet made, one that will eventually cover something like a third of the entire sky. The filaments themselves were harder to confirm than the nodes because they are faint. The gas strung along them is hot and extraordinarily thin, and it does not glow brightly enough to image directly at large distances. In 2019, a team led by the astronomer Anna de Graaf took a statistical approach instead, stacking the signals from over 1 million pairs of distant galaxies and looking for the subtle imprint the intervening gas leaves on the oldest light as it passes through, a distortion known as the Sunyaev-Zeldovich effect, after the physicists who predicted it. Averaged across 1 million pairs, the imprint appeared. The threads connecting galaxies are really there, and they are made of something. There are also structures in these maps that the theory has trouble accommodating, and they deserve mention because they are unresolved rather than settled. Standard cosmology places a rough upper limit on how large a coherent structure can be, somewhere around 1.2 billion light-years. In 2021, a doctoral student named Alexia Lopez, working at the University of Central Lancashire, identified an arrangement of galaxies traced by quasar absorption that appears to span nearly 3 times that limit. It was named the Giant Arc. In 2024, the same researcher reported a second structure at a similar distance and only a short, angular separation away, a ring roughly 1.3 billion light-years across. The honest counterweight arrived quickly. In 2025, an analysis using a large cosmological simulation argued that patterns of this scale turn up by chance in an ordinary universe, and that the human eye is unusually good at finding arcs and rings in scattered points. That argument may well be correct. The question is open. And in 2014, an analysis led by the astronomer Brent Tully at the University of Hawaii took a different approach. Rather than mapping where galaxies are, his team mapped where they are going, tracing the velocity flows of tens of thousands of galaxies to find the boundaries where matter stops falling one way and starts falling another. By that definition, our galaxy turns out to belong to a supercluster roughly 520 million light-years across, containing perhaps 100,000 large galaxies. They named it Laniakea, from Hawaiian words meaning immeasurable heaven. We are not at its center. We are near an outer edge, drifting inward, with everything else toward a region of concentrated mass, in the direction of the constellation Centaurus, which was named the Great Attractor before anyone could see what was there, because dust in our own galaxy's disk blocks the view. So this is the true architecture, a network of threads, a scattering of knots where the threads cross, sheets stretched between them, and filling everything the threads do not, an emptiness that constitutes the substance of the universe by any measure of volume you care to apply. We have described the web. Now we go into one of the holes. In 1981, 4 astronomers, Robert Kirshner, Augustus Omler, Paul Schechter, and Stephen Schechtman, were conducting a redshift survey aimed at a different question entirely. They were sampling galaxies in several directions to study how matter was distributed, and one of their sample fields pointed toward the constellation Bootes, high in the northern sky. The galaxies in that direction had a gap in them, not a thin gap, not a statistical dip. Across a great range of distance, in the region roughly 700 million light-years out, the galaxies they expected to find were absent, and they stayed absent through a span of the survey so large that the authors initially had to consider whether something was wrong with the observations. Nothing was wrong with the observations. They had found the Bootes void. It is a roughly spherical region of the universe, on the order of 250 to 330 million light-years across. Take that number seriously for a moment. Light entering one side of it needs 250 million years to reach the other. The dinosaurs had not yet appeared when a photon, now leaving the far edge, began its crossing. At the average density of the universe, a volume that size should contain somewhere around 2,000 galaxies. Careful searches, since its discovery, have found around 60, in a region large enough to hold 2,000. And even that count overstates the emptiness of the interior, because a number of those 60 are strung along a rough filament that appears to run through the void, rather than sitting in the deep interior. There are stretches inside it, tens of millions of light-years across, in which nothing at all has been detected. The obvious first suspicion, when a survey returns a hole, is that the survey has a hole in it, a patch of sky observed on a bad night, a gap in the coverage, a selection effect that quietly removes faint objects at a particular distance. The discovery team and everyone who followed spent years testing exactly that, extending the survey, sampling more directions through the region, checking with independent instruments and independent methods. In 1987, Kirshner and his colleagues published a substantially larger follow-up study confirming the structure and refining its dimensions. Later wide-field surveys covering the same part of the sky found it again. The void survived every check. It is not an absence of data. It is data about an absence. And the emptiness has since become useful, which is a strange thing for nothing to become. Because a void contains so little matter, light passing through it is bent in a measurably different way than light passing through a filament, and the shape of a void, as it appears on the sky, can be compared against its depth along the line of sight to test whether our distance scale is behaving correctly. Voids are now used as cosmological instruments in their own right, and there are researchers whose entire careers concern regions that contain almost nothing. The astronomer Greg Aldering, considering what this would mean for anyone living inside such a place, made a remark that has been repeated ever since. His point, in substance, was this: if our own galaxy sat at the center of the Boötes void, we would not have discovered that other galaxies existed until well into the 20th century. That is not rhetoric. It is a calculation about telescope apertures and apparent magnitudes. Think about what it actually claims. Edwin Hubble established the existence of galaxies beyond our own in the 1920s using a 100-inch telescope on Mount Wilson, and he could do it because Andromeda is 2.5 million light-years away, close enough to resolve into individual stars. Move the Milky Way into the center of Boötes, and the nearest comparable galaxy is not 2.5 million light-years off. It is on the order of 100 million. Everything beyond our own spiral becomes an undetectable smear. A civilization there would develop physics. It would develop chemistry. It would work out the life cycle of stars, and the age of its own sun, and the structure of the atom, and it would conclude, with every observation it was capable of making, that its galaxy was the universe, and that beyond it there was nothing. It would be wrong. It would also have no way to find out. We came uncomfortably close to that condition ourselves, and this is where the story turns back toward us. There is a body of work, beginning with a study by the astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, published in 2013, arguing that we are ourselves sitting inside an underdensity, a local hole. Their infrared galaxy counts suggested that the region around the local group, out to a few hundred megaparsecs, contains meaningfully less matter than the cosmic average, with a density contrast reported as roughly 0.46, plus or minus 0.06. If that is right, it has consequences beyond geography. Matter would tend to flow outward from such a region toward the denser material surrounding it, and that outflow would inflate the apparent expansion rate we measure locally by something in the region of 11%. Some researchers have argued this could account for a substantial part of the disagreement over the expansion rate we discussed at the beginning. The persistent gap between the value measured from the oldest light and the value measured from nearby stars. In that reading, the tension is not new physics. It is an artifact of the neighborhood, the honest counterweight. And it is a serious one. A field-level analysis published in 2025 using a large catalogue of galaxy distances measured by a different technique, prefers a local void far smaller than the one that argument requires, something around 1/10 of the necessary size. The claim of a large local hole remains contested. It is a live argument in the literature, not a settled result, and you should hold it as one. But the possibility itself is the point. There is a genuine, published, actively debated hypothesis that the reason our measurements of the universe do not agree is that we are looking out from inside an emptiness and mistaking its properties for the properties of everything. It is also worth understanding that a void is not a static container. It is an active process, and the process runs one way only. Gravity is a positive feedback mechanism at cosmological scale. A region with slightly more matter than average pulls in more and becomes denser and pulls harder. A region with slightly less exerts a weaker pull than its surroundings, so its contents drift outward toward the denser walls, and it becomes emptier, and its pull weakens further. Run that for 13 billion years, starting from a nearly uniform beginning, and you do not get a mild variation in density. You get filaments, and you get holes, and the holes are still opening. Boötes was never scooped out. It was outvoted. Every galaxy that might have formed inside it was drawn away to the walls before it could. And what remains is not the residue of a catastrophe, but the natural endpoint of a region that started with slightly less than its neighbors and lost the argument for the entire history of the universe. The voids are not rare, in any case. Boötes is simply the one that got a name early. The Sloan survey and its successors have catalogued voids in the thousands. There is a candidate underdensity associated with an unusually cold patch in the oldest light, sometimes called the Eridanus supervoid, though whether it explains that cold spot is disputed. There are void catalogues now containing so many entries that they are handled statistically rather than individually. And the galaxies that do live inside voids appear to be different from the ones out here. Studies of void galaxies consistently find them to be smaller on average, bluer, richer in gas, and apparently slower to develop, as though, having no neighbors to interact with and no dense environment to strip their material away, they have simply been left to proceed at their own pace, unfinished, for the entire age of the universe. They are not dying. They are not depleted. They are just alone, and they have always been alone, and nothing has ever arrived to change them. Consider what a void does to time. In a filament, galaxies encounter one another. They merge. They trigger bursts of star formation. They strip each other's gas. They build up mass. Structure has a history there. In the deep interior of Boötes, nothing has encountered anything. There is no history. There is a volume the size of 250 million light-years across, in which, for 13 billion years, the principal event has been the slow, continued thinning of what little was there to begin with. No collisions, no mergers, no shock fronts, no starbursts, no spiral arms winding up, no clusters assembling, no supernova blowing a cavity into a cloud that never existed in the first place. No arrivals. Nothing has ever come from anywhere, because there is nowhere near enough to come from. That is the deepest emptiness we have found. And we have not found the bottom, because we have not looked everywhere, and the volume left to look in is almost all of it. Everything so far has concerned the space between objects. Now we go inside them, because the emptiness does not stop at the surface of things. It goes all the way down, and the numbers there are worse. In 1909, at the University of Manchester, a physicist named Ernest Rutherford set two of his colleagues, Hans Geiger and Ernest Marsden, an experiment he did not expect to produce anything interesting. They were to fire alpha particles at a sheet of gold foil a few thousand atoms thick and record where they landed. The accepted model of the atom at the time treated it as a diffuse sphere of positive charge with electrons distributed through it. Under that model, the particles should have passed through with only slight deflections, the way a bullet passes through fog. Most of them did, but a very small fraction, roughly 1 in 8,000, came back, not deflected, reversed, bouncing off something and returning toward the source. Rutherford later said it was as though a shell fired at tissue paper had rebounded and hit him. The conclusion he published in 1911 changed the physical picture of matter permanently. The positive charge of an atom is not spread out. It is concentrated in an extraordinarily small central object, and the rest of the atom is essentially unoccupied. Here is the scale of it. A typical atom is around 1/10 of a nanometer across. Its nucleus is around 100,000th of that. That ratio, 1 to 100,000 in length, becomes 1 to 1,000 trillion trillion in volume. Now I want you to build something, and we will stay inside it for the rest of this. Imagine a cathedral, a large one, 100 meters from the entrance to the far wall, with a vaulted ceiling far overhead and stone floors and total darkness inside. You are standing at the door. Somewhere near the middle of that cathedral, suspended in the air, is a single grain of rice. That is an atom. The grain of rice is the nucleus, where essentially all the mass is, where the protons and neutrons sit, where the thing you would call the substance of matter is located. Everything else, in that vast, dark building, is the region the electrons occupy, and electrons have so little mass that they contribute almost nothing to the weight of the whole. Your hand is made of these. So is the chair, the floor, the air, the earth. Every atom in every object you have ever touched is a cathedral with a grain of rice in it. And the reason your hand does not pass through the table is not that the two objects are solid. It is that the electric fields of their outermost electrons repel one another. You have never touched anything. You have been held a fraction of a nanometer above every surface of your entire life by a force, and the surfaces themselves are hollow. There is an objection to this picture, and it is a fair one, so it belongs here rather than in a footnote. A physicist would tell you that the cathedral is not really empty, because the electron is not a tiny ball orbiting at the walls. It is a distribution, a standing pattern of probability filling the whole volume, with no definite position until something interacts with it. In that sense, the atom is entirely occupied by electron, wall to wall, and nothing about it is hollow at all. That is correct, and it does not rescue us. Because when we ask how much matter there is, we are asking about mass, and the mass is not in the pattern. An electron is roughly 1/2000th the mass of a proton. Take a hydrogen atom, spread its electron through the entire cathedral as a cloud, and 99.95% of the weight of the building is still that one grain in the middle. The occupancy is real. The substance is not distributed with it. So what happens if you take the emptiness out? We know, because the universe does it. When a massive star exhausts its fuel and its core collapses, the pressure becomes sufficient to force electrons and protons together into neutrons, and the entire structure of separated cathedrals collapses into contact. The result is a neutron star, an object typically around 20 kilometers across, containing more mass than the Sun. A single teaspoon of that material would weigh, by standard estimates, something on the order of 1 billion tons. Do it to the planet, and the Earth, 12,500 kilometers of rock and iron and ocean and atmosphere, comes down to a sphere roughly 300 meters across. Everything under your feet, every mountain range and every trench, every continent and every drop of every sea, reduced to something that would sit inside a city park. Compress it further, past even that, and the Earth would fit inside a marble before the geometry of space closed over it entirely. Apply the same operation to us. Take every human being alive, all 8 billion of us, and remove the empty space from every atom in every body, packing the nuclear material together at neutron star density. The volume that remains is, by these estimates, roughly that of a sugar cube. The entire species. Everyone you have ever loved. Everyone who has ever hurt you. Everyone whose name you know, and the billions whose names you do not. A cube you could hold between 2 fingers, if it did not weigh as much as a mountain, and immediately fall through the floor and through the planet. Now do it to everything. This calculation is rough, and it should be treated as an order of magnitude rather than a measurement, because the inputs themselves carry uncertainty. But it can be done, and the answer is worth the arithmetic. Take the estimated mass of all the ordinary matter in the observable universe. Every star, every planet, every atom of gas in every filament and cloud, every grain of dust in every galaxy, out to the edge of what we can see. Compress all of it to the density of an atomic nucleus. You get a single sphere, something like 7 astronomical units across. That is smaller than the orbit of Jupiter. Every atom that exists in the observable universe, all of it, gathered into a ball that would fit inside our own solar system, with room to spare. Not the galaxy, not the local group, not the cosmic web with its filaments and its voids stretching 93 billion light-years from side to side. A ball you could put inside the orbit of one planet, in one ordinary system, on one arm of one galaxy, in one small group, at the edge of one supercluster. That is the actual quantity of material the universe contains. Everything else, every distance we have crossed in this descent, from the gap between 2 stars in a cluster core to the 250 million light-years of nothing inside Botes, is the space that material has been distributed through, which brings the cathedral back, because it has stopped being a metaphor about atoms. The cathedral is the correct picture at every scale we have looked at. Zoom out from the atom to the solar system, and the sun is the grain of rice, and the cathedral runs out past Neptune. Zoom out to the galaxy, and each star is a grain, and the cathedral is tens of trillions of kilometers wide. And there are hundreds of billions of grains scattered through a building so large that light takes 100,000 years to cross it. Zoom out to the cosmic web, and the galaxies themselves become the grains, strung along the walls of a structure whose interior spaces are so vast that we had to invent a separate word for them. The same building, over and over, at every magnification we have been able to reach. And in the deepest voids, there is no grain at all, only the cathedral. Everything described so far is a snapshot. It is the arrangement as it stands, and it is not stable, and it is not moving in the direction anyone would prefer. In 1998, 2 independent teams, one led by the astrophysicist Saul Perlmutter at the Lawrence Berkeley National Laboratory, the other by Brian Schmidt and Adam Rees, were measuring the brightness of distant exploding stars in order to determine how quickly the expansion of the universe was slowing down. Everyone expected it to be slowing down. Gravity pulls, matter attracts, and the only real question was whether the deceleration was enough to eventually reverse the expansion or not. The supernovae came back too faint, consistently, at high distance, dimmer than they should have been. The expansion is not slowing. It has been accelerating for the last several billion years, driven by something that behaves like a property of space itself, which we call dark energy, because naming a thing is not the same as understanding it. The measurement earned the 3 of them the Nobel Prize in Physics in 2011, and it left cosmology with a component that constitutes roughly 7/10 of the total contents of the universe, and about which almost nothing is known. Whatever it is, its effect on the emptiness is direct, and it compounds. As space expands, everything not bound together by gravity is carried apart. Galaxies inside a cluster stay put relative to each other, because gravity there is winning locally. Everything beyond that scale separates, and the separation accelerates, and the density of matter per unit volume drops accordingly. The universe is not merely empty, it is emptying. The average density of ordinary matter today is lower than it was 1 billion years ago, and it will be lower still 1 billion years from now, and there is no mechanism in the current picture that reverses this. Now the part that is easy to miss and difficult to hear. The observable universe is growing. Every year, light from slightly more distant sources has had time to reach us, so the sphere of what we can see gets larger. But the reachable universe, the set of places we could in principle ever send anything to or ever receive a reply from, is shrinking, and it has been for a long time. The reason is that the expansion carries distant objects away faster than a signal can close the gap. Beyond a certain distance, the space between us and a galaxy is being added faster than light can cross it. A radio message sent today towards such a galaxy will never arrive. Not slowly. Not eventually. Never. That boundary sits at a redshift of roughly 1.6, which corresponds to a distance well inside the edge of what we can see. The consequence is stark. The overwhelming majority of the galaxies visible in a deep field image are already permanently beyond contact. We can watch them. We are looking at light they emitted billions of years ago, but there is no possible action, at any point in the future, by any civilization, with any technology, that could reach them. They are visible, and they are gone. Those are not contradictory statements. And the boundary keeps tightening. Galaxies currently just inside it will cross it. Nothing crosses back. There is a further complication that is genuinely unsettled and worth stating carefully, because it is the most active argument in the field right now. Analyses from the Dark Energy Spectroscopic Instrument, released in 2025, report a preference for dark energy that changes over time rather than staying constant, at a statistical significance that varies between about 2.8 and 4.2 standard deviations, depending on which catalogue of supernovae is combined with the galaxy data. That is suggestive. It is not yet decisive, and several independent teams are working on whether it survives. If it holds, the future changes. A weakening dark energy would slow the isolation. A strengthening one would accelerate it, potentially to an extreme. We do not know which, and anyone who tells you confidently is going beyond the evidence. What is not in doubt is the direction things have been running for the last several billion years, and the far future it implies. Star formation itself is already in decline. The peak epoch of star birth in the universe occurred roughly 10 billion years ago, and it has been falling since. Analyses of survey data suggest that something like half of all the stars that will ever exist have already formed. The gas needed to make new ones is being consumed, locked into stellar remnants, or blown out into a medium too thin ever to collapse again. We are not living at the beginning of the universe's productive period. We are living well after it. In 2007, the physicists Lawrence Krauss and Robert Scherer worked out what an observer in the far future would be able to see, and the paper has an implication that ought to be more widely known than it is. Given enough time, hundreds of billions of years, the local group will have merged into a single elliptical galaxy, and every other galaxy will have receded beyond the horizon of contact and been redshifted into undetectability. The oldest light will have been stretched until it is unmeasurable. The evidence for expansion will be gone. The evidence for the Big Bang will be gone. Astronomers on that world will look up, and they will see a single island of stars surrounded by perfect blackness, and they will conclude, carefully, rigorously, using good instruments and correct reasoning, that their galaxy is the entire universe, and that it is static and eternal. They will be wrong, and every piece of evidence available to them will support the wrong answer, which means the emptiness does something worse than isolate. It erases. The universe is not only dispersing its contents beyond reach, it is destroying the record of ever having had them, and the window in which the true history is legible from the inside is finite, and we are currently inside it. And the grains go out. The smallest and most frugal stars, the red dwarfs, are expected to burn for something on the order of trillions of years, which is roughly 100 times the present age of the universe. But that is a limit, not a reprieve. After it, on timescales that make trillions look brisk, what remains is white dwarfs cooling toward the temperature of the surrounding space, neutron stars doing the same, and black holes evaporating so slowly that the numbers involved stop being writable in ordinary notation. The cathedral does not fall down. Nothing dramatic happens to it. The grain of rice at the center simply stops giving off light, and the building continues exactly as it was, at the same size, in the same silence, for a length of time that dwarfs everything that came before it. We are living in the era when it is still possible to know. It is a narrow era, and it is early, and it is bright. So go there. One last movement outward, and then we stop. Leave the local group. Leave Laniakea. Cross the filament, out past the last thin scattering of dwarf galaxies clinging to the wall, and keep going until the wall itself has faded behind you and there is nothing ahead. Then travel for another 100 million years at the speed of light, and stop and turn around. This is the interior of a void, and it is where the universe keeps most of itself. There is no sky here. There are perhaps a few dozen smudges scattered across the whole sphere of view, so faint that you would need an instrument to know they were there at all. And each one is a galaxy of 100 billion suns, rendered by distance into something less than a rumor. Between them, in every direction you could choose to look, there is a volume of space so large and so nearly vacant that the phrase 1 atom per cubic meter overstates it. Nothing is happening. Nothing has happened here since the universe was young, and the reason is not that something ended, it is that nothing ever began. We do not know how much of this there is. We know the observable portion, and we know that the observable portion is not the universe. It is the distance light has managed to cover since it was released, which is a fact about the age of the cosmos and the speed of light, and nothing whatsoever about the size of the thing itself. Space may continue for a very long way past that boundary. It may continue without end. There is no measurement that can return the answer, and there may never be one, and physicists who work on the question say so plainly. What we can say is that in every direction we have been able to check, out to the limit of what light can show us, the arrangement is the same. Threads with a little matter in them, cathedrals with almost nothing in them, and the cathedrals go on past the edge of the map. There is a way of hearing all of this as bleak, and I want to argue against it, briefly, because I do not think the arithmetic supports it. An empty universe is not an indifferent one. Indifference requires a position. The voids have no position on us. What the emptiness actually establishes is scarcity. That matter organized into anything at all is the rarest condition available. That the circumstances required to produce a grain, rather than a cathedral, almost never occur, and that when they do occur, the result is temporary. Rarity is not a reason for despair. It is the entire basis of value. If this walk outward has been worth your time, I would be grateful if you left a like and told me in the comments which of these distances was the one that got to you, and subscribed so you can come with me the next time we go out into the dark. Thank you for staying this far. Here is where it leaves us. You are standing inside the densest thing you will ever encounter, on a planet that is a rounding error, orbiting a grain of rice, in a building so large that light needs 100,000 years to cross it, in a neighborhood of buildings separated by gaps that make the buildings look small. And every atom of you, the iron in your blood, the calcium in your bones, the carbon in every cell, is nuclear material that was assembled inside a star and thrown out when that star died, gathered here by gravity into an arrangement that can look up and do the arithmetic. The universe is not mostly stars. It is not mostly galaxies. It is not mostly anything you have seen a photograph of. It is mostly the space where those things are not. And in an enormous dark cathedral, at some unremarkable point along the wall, On one grain among the scattered grains, something is awake and paying attention, and it has been for a very short time, and it does not know how long it has, and the light it is looking by is already old,